I will tell you that I am from MJP Royalkhand University, Bareilly. That is Mahatma Jyotiba Phule Royalkhand University. And this university, you see, this is situated in Bareilly. And this university has, the jurisdiction of the university is 9 districts, spread over 2 commissionaries, Moradabad and Bareilly. And this university has a campus as well as the affiliated colleges. At campus we have about 6,000 students, and in the colleges it is about 4.5 lakhs students in 350 colleges. And the university has a different subject, almost all subject. Campus is spread over 207 acres. And you see, it was established in 1975. Campus came in 1985, and it is B plus NAC accredited. The university has been ranked 2nd best in the university all over the Uttar Pradesh, and it promotes the education in higher education in all walks of life. That is in all faculties we have, including engineering, medical faculties. Now, about this talk, my talk. And before this MJP Royalkhand University, I was at Jamia Millia Islamia, New Delhi. It's not Jamia Millia Islamia University, because Jamia itself means university in Urdu or Arabic. So that's why we do not put university with these words. And you know, this university was established, Jamia Millia, in 1920. And you know, the aim of the university was that when there was a Khilafat movement or Gandhiji's non-cooperation movement. And the movement was that we have to boycott the British education. So when you boycott the British education, you must have your own institutions. So under that context, the Jamia Millia Islamia, the Kashi Vidyapeeth and the Shanti Niketan came into existence. And this university has witnessed more than 100 closed-down meetings under the leadership of Mahatma Gandhi at his campus. So this university played a very important role in Indian freedom movement. This university has all faculties, including medical, engineering, and famous mass communication research center, and about 22 center for excellent learning. And out of that, we have 4 or 5 centers from religion to the science, the Center for Interdisciplinary Research. And very recently, we have created Center for Nanoscience and Nanotechnology. Before that, there was already a group of material science group. I was heading that group, and in my group, we have studied the number of materials like amorphous semiconductors, superconductors, carbon nanotubes, conjugated polymers, and laser materials. So this is the my group, and these are the people who are working at present at different institute, different in our collaboration. And now, so the center was created. Center has very specific aim about the researches in different fields, and particularly device-oriented fields. And we are working particularly on carbon nanotubes, zinc oxide nanostructures, chalconite nanostructures, modeling and simulation. Of course, that is dynamical response of non-linear vibrations in single-wall carbon nanotubes. So, means in inaugural, I just some means discussion on modeling and simulation, but we are also doing the modeling and simulation, which is very important. Now let us start by lecture. See, science. Science is a philosophy. So nanotechnology. And what is the philosophy of nanotechnology? Real, small, is big. This is the philosophy of nanotechnology. How small is big? You see, that is, you see this radio. This is the radio actually. See, 40 years back, when we were children, my grandfather used to take to somebody's house, and he was saying that he is a landlord, we are going to a big man. So I used to ask, how he is big? How can you scaling him? measuring it. Then he told he had a big radio in his house. After that, what happened? Then the people attached a gramophone to this radio, and whenever you enter in the drawing room, the 1.5 meter long radio come gramophone means that is record player placing in the drawing room. So very people used to have these radios. But what is scenario today? Who is big? The big is that who has a small watch in his hand. The watch has camera, the watch has time, it has internet, everything and what not in that. So, who is big? Responsible. So, this is the philosophy of nano. Now, this is now we have three important technology, bio, info, nano, and now there is a convergence of these technologies. Now, just see about this nanotechnology that the Feynman in 1959, he said, I do not speak against the maneuvering of the things atom by atom. Means we can manipulate the atoms, we can maneuver the atoms, but in 1959 there was no name of the nanotechnology. It is the perception of Feynman that it is possible. So it is his idea. And this word nanotechnology was invented by Takasaki, and then it is popularized by Dexler in his book, Engines of Illusion. Now, it's an interdisciplinary area. It is all walks of life. In walks of life means materials, material science, physics, chemistry, mathematics, engineering, medical sciences, economics, and sociology. Then what this economics and sociology will do in that? Yes, it is very important that the sociology means what is the impact of this technology on society, what is the societal impact. That is a very important point. Economics. See, what we are doing technology simply to earn money. So we should have economics of that. So that is a interdisciplinary research. Now next is, you see, it is from early days. You see this cup, it is placed in the British Museum. The cup has different colors of same material. And then we can explain nowadays that is this colors. And also, once Michael Faraday, he was roaming in the church and he saw the different colors, on the church window. And then why so? That is, he could not explain. He was a great scientist. Nowadays, we can explain the colors, images, and all those things. Now, simply we have these nanostructures in nature also. That is very, that is, you can say the nano glow, nanostructures. Okay. And a lot of applications of nanotechnology in all walks of life, whether it is the medication, is a textile, metals, and sensors, and in all electronics we have, surgery we have. So number of applications of nanotechnology in your daily life. Now let's see about the nano scale. Particularly, all people are from science background. The nano means 1 nanometer is a billionth part of a meter, or you can say it is a 10 millionth part of or means the millimeter. That's so small. Similarly, human hair. Sometimes we say, oh, human hair is very thin like that. It's not thin, it's very thick. It is 100,000 nanometer. The cell, particularly the biologists, they used to frighten us. Oh, we are working on cell, on human cell, and that's a very small. The cell is not small. Cell is very big. It is 10,000 nanometer. So they were thinking that all cell is small. DNA of course it's a 2.45 nanometer. That very well comes in nanometer regime. The nanometer things is 1 to 200 nanometer. Beyond that, you are not having the nano things. The 10 hydrogen atoms you put means side by side, then it constitutes 1 nanometer. So this is the size all like that. So particularly the human cell is a very important thing that it's very big. Now, so in the first slide I have told you the philosophy of nanotechnology where small is The second definition actually about the nanotechnology, somebody asks you, what is nanotechnology? The only one line answer of the nanotechnology is that nanotechnology is nothing, it is simply the size. That's all. This is the proper definition of nanotechnology, it is the size effect. How do we see the size effect? Now you see the melting point. If you ask a chemistry person, what is melting point? Melting point is a constant quantity or barrier. They will say it's a constant. But you see, the melting point is not constant. The melting point of the gold is 1064 degrees centigrade. But when the the gold particle at nanoscale, it will melt around 5 degrees centigrade. Now, other you see, this is the silver. What is the color of silver? It's white. It is only white when you see in bulk. But if you go down, you reduce the size. It is 20 to 40 nanometers. It is gray. More than 50, it is white. And if it is less than 50, it is black. The color of the silver is black when you are having particle size less than 50. So, and it is not by dirt or any other thing. So this is about the colors are changing with the change of size. The melting point is changing. Now there is another thing you can just see this one slide. This slide I have prepared. That is, to explain like that. This is the rubber ball. You just throw on that. It will fall. It will fall down like this. But if there is a dust on the rubber ball, that dust will not fall down, rubber ball will fall down. Why? The size of the rubber ball is much bigger than the size of the ball particles. That's why it will come down. And the size of the dust is smaller than these particles, so it will be something stable. And now suppose you put the nano paints on the wall, nothing will stay. Water drop, dust, anything. So this will, again you see the size of it. And this is similar to that. It's a very good news for ladies. Soon we will have the nano cosmetics. They are coming. They will come in the market. Nano paint already are. They have one company in India. ICAN is producing the nano paints. So it is just, you see, nanotechnology is nothing. It is simply the size effect. In this bottle, we have number of same material in different sizes. We have different colors. So this is again. So how to explain is that when the particle size decreases, the band gap increases and optical absorption spectra from red to blue. So color changes. This is the explanation how the color is changing of the same material in different sizes. Now let's see. So this is about the color change. Now this is again the GMR effect, the Nobel Prize given up to 2007. That is so this is a GMR effect, giant magnetoresistance. In here also the things depend on the size. When you measure the resistance, then measure the magnetoresistance, and then again reduce the size, the magnetoresistance changes drastically. When resistance changes drastically, there is a lot of change in the current. Basis on that, we have a GMR effect, and this 2007 Nobel Prize was given, and then nanotechnology gives sensitive readout for computing hard disk. So this is the first application, important applications. Now come to the other example of size effect. The other example of the size effect, you see the carbon. Carbon is a very important material. You have a chemistry of carbon. And in carbon, you have 3 materials, diamond, graphite. Then there was a discovery of buckyball in 90 or 91. Buckyball was discovered. Buckyball was discovered not during the time of nanotechnology. People were not knowing the nanotechnology, but it was discovered during the era of super nanotechnology. There was a time when everybody was talking to superconductivity, and in superconductivity it was discovered, and then after that we have other nanotube and graphene. Now, so discovery. So graphene was discovered. Is a structure of the this buckyball was discovered. The fullerene, we say, it is a 20 hexagon and 12 pentagons. There are a lot of things about the structures and all those. I will not go in detail that. But the most important property of this buckyball is it's highly electronegative. When it is highly electronegative, it can combine with the first group element, potassium and rhodium, and they can combine and then they become superconductor. Neither carbon is superconductor nor this buckyball is superconductor, but when you combine, these compounds are superconductor. So this is the discovery of buckyball, and after that you see what happened in 1991. See, the scientist is in. See, generally, see, the chemists are very fond of two things. One is substitution reaction, other is to analyze the byproduct. Once I was delivering a lecture, an old chemistry professor was very annoyed. How you say like that? How are you saying that we do only two jobs? So I told, sir, physicists are doing only one job, and the physicists are doing only conduction mechanism, nothing else. No, whether it is a superconductor, it's a amorphous semiconductor, conducting polymers, nanomaterials. We simply doing the conduction. Then he became very. We are doing two, you are doing one. So this is the actual point actually there. So this was discovered. The Isima discovered a new material from the byproduct of fullerene, and he found that a new material which is different in molecular weight, and they analyzed the structure. The structure was a cylindrical structure, and this cylindrical structure is known as carbon nanotube. Please must remember this carbon. It's my opinion that 60 to 70% applications in nanotechnology are from carbon nanotube. Though nanotechnology nowadays is becoming fashion. Everybody is doing nanotechnology. If you talk what I am doing, I am doing nanotechnology. What is the size of particle? 500 nanometers. Well done. Now, 500 nanometer, you are doing nanotechnology. So, so this is the thing actually. So about this carbon nanotube business is a very important, and particularly in my group, we have studied the carbon nanotube in a big way. And these carbon nanotubes, they are the first mechanical strength. You see, our director, this book sir has a from mechanical engineering plant. Sir, it is the carbon nanotube is 100 times stronger than steel. It's a very strong material, and then it is 6 times lighter than steel. And if you see, the conductivity is also very high. It's about means much better than the copper actually. And thermal conductivity is also 5 times better than copper. You see such a material which is having such a strong material. Generally, these very strong materials, they are not a good conductor. But this material is a good conductor, very good conductor also. That's why these type of properties we do not find in other materials. That's why this material is known as the material of 21st century. This material, these carbon nanotubes are two types. It's a single wall carbon nanotube and multi-wall carbon nanotube. Single wall, only single cylinder. Multiple wall, cylinder inside the cylinder. And the structure of multi-wall is very complex. So, it's very difficult to handle theoretically. You are not doing the modeling and simulation of the multi-wall carbon. Single wall. Single wall is single wall. Then it is easy to do the mathematical analysis and modeling simulation and many things you can do with this single wall. But if you prepare experimentally the multi-wall carbon nanotube, it is easier to produce but it is very difficult to produce single wall carbon nanotube because of its diameter. A diameter is only 1 to 4 nanometers. So very difficult to control this diameter. And so these things about single wall, again it is three type. It is armature, zigzag, and Chirac vector. These are the different type of these single wall carbon nanotube, and one is metal, semi-metal, and then armature. So this is now what we are doing actually. See, synthesizing the carbon nanotube. There are number of methods, and here the important methods are chemical vapor deposition, arc discharge, and laser evaluations. We are synthesizing by chemical vapor deposition, and different techniques required for different tubes, like at least single wall carbon nanotube, multi-walled, and aligned carbon nanotube. Now you see type of carbon nanotubes, then the catalyst used. See, I want to tell you here, the cooking temperature or the synthesis temperature of these carbon nanotube is very high, 1200, 1500. So you are handicapped that you cannot grow carbon nanotube on polymers, on glass like that. The glass will melt before synthesis. So this is the problem. We are synthesizing carbon nanotube on silicon substrate. But if you coat a catalyst over there, the synthesis temperature goes down. So particularly those who want to do research, is the topic. What is the topic? To search a catalyst. This is a chemistry thing actually. To search a catalyst by which you can grow the carbon nanotube lower and lower temperature. This is a research problem. And also there is is yield and purities, and there is another problem, means research problem, how to align carbon nanotubes. The alignment is very important for particular applications like field emission and other things. So we have grown carbon nanotube. This is arc discharge method. You can find at the books that we create the arc between the two graphite electrodes in helium atmosphere, and then we can synthesize the arc discharge. Similarly, the laser ablations at 1200 degrees centigrade in the oven, we are means a pulse of continuous laser is used for vaporize the graphite sheet, and we are getting the carbon nanotube. Now what we are doing, just see growth of the carbon nanotube. We are taking the silicon wafer and its cleaning of the wafers and all those things, and then finally we coat the on silicon wafer the catalyst. Maybe the whole film, or maybe the dots you can put of catalyst. Maybe gold, maybe iron, nickel, or any other catalyst we are coating on that. After coating, we are taking to this means material into this CVD system, that is LPCVD, low pressure vapor, low pressure chemical vapor deposition, and here we are using the ammonia, hydrogen, acetylene gases. Acetylene is the source gas, and the flow and many other parameters we are controlling, and then we are growing the carbon nanotube. This is the structure grown by our laboratory. This is a network of their diameter is about 30 to 50 nanometers. And after that, again, this is a multi-walled carbon nanotube, but single tube, and here this is the 44.5 nanometer, like this we are growing. And then this is the aligned carbon nanotube. Please see, this is a very beautiful picture, aligned. And it's very difficult, and there is no set formula to grow the aligned carbon. So this is from our lab actually. And now again, that is, we use different catalysts and different multi-walled carbon nanotube we have grown, and on different substrate we have grown, and that is the different technique we have used. These are all these pictures from our lab. That is the last slide you see here, the forest of the carbon nanotube. It is required for field emission properties. Now also there are a number of things we have developed, and we have characterized by the SAM, TAM, and then the Raman spectroscopy, these carbon nanotubes. Now, there is an indigenous method we have developed. We were working on ECR plasma etching system in Netherlands before 97, 98. We have converted this machine into, that is, we name it ECR-CVD, electron cyclotron resonance chemical vapor deposit system. And by this actually we have grown this actual machine, and we have grown the carbon nanotube at somewhat lower temperature, around 500 degrees centigrade. And this is the network of the, now again, I told that these carbon nanotubes are two types: single wall carbon nanotube, multi-wall carbon. It is easier to grow multi-wall. It's very difficult to grow single wall carbon nanotubes. And we took a challenge of that, and the Department of Information Technology that they granted a project about 4 crores actually for this purpose, and we have constructed a laboratory for that, and finally we have grown the single wall carbon nanotube. And so I have already told you the single wall carbon nanotube, that is just one layer of carbon atoms. Its diameter is around 1 to 4 nanometers, and that is for that we have used PECVD, plasma enhanced chemical vapor deposition system, for single wall carbon nanotubes. And then this machine from Exitron, we have used this machine and constructed the laboratory. This is the first room of the laboratory. Here we have installed this PECVD system, and this is the second room. We have the gases, pumps and all those things. This is the third room where we have the cylinders, gases systems, and on it is on the roof, that is the exhaust system. And these are all systems where, because we are using the hydrogen over here, so it's a very dangerous to use hydrogen, then we have all sensors and all those things for safety purposes. So it is a laboratory with 3 rooms and a roof we have used for that. And from this lab, we have synthesized the single wall carbon nanotube, and these are the single wall carbon nanotubes about you can say this is 2 nanometers, and then lot of work, lot of permutation, combination on different parameters we did it, and then we have grown number of these sets of the carbon nanotube, and finally we have analyzed these carbon nanotubes, and then we have come across about the carbon nanotubes of 1 nanometer especially, and then also the 2 nanometer, and still work is going on to grow that 3 nanometers like that. And now again you see the aligned carbon nanotubes. If you see the literature, hardly you will find such tubes aligned or multi-wall carbon nanotube. It is from the same machine. The machine can grow single wall, multi-wall, and also the graphene. This machine PECVD. You see the pictures, so beautiful pictures. These are diameter is about 20 nanometers, 30 nanometers like that, and so clean, so clear actually for alignment purposes. And there is no set formula for that. It depends upon your skill. Or this is just see, these are all carbon nano, multi-wall carbon nanotube. And again, so these are the synthesis from our lab of single wall carbon nanotube, and we are utilizing for these things for study of field vision, also the sensor purposes, and also the see the atmospheric pollutants means sensor like that. These carbon nanotubes are very important, and then that is, it has applications in nanoelectronics, hydrogen storage, and medical applications. In nanoelectronics, you see some applications like this. See, first thing you see the AFMT. It is so strong actually, it's mechanically 100 times stronger than steel, so it can be used for AFMT. As you know, in the older time we were having gramophones, and gramophones we are using the steel needle, and our grandfather used to say, you sharp this after playing 2-3 records. They were asking to sharp the needle by just rubbing on the stone. So, but there is no need to rub. We have a carbon nanotube steel. It's 100 times stronger than steel. And also, So there was a revolution. In the morning I told you there was a revolution in 1957 when transistor got birth and your big radios converted into transistors. And ultimate of the nanotechnology is that we have to go smaller devices. So when you have smaller devices, your transistor PNP, NP will not work on any transistor. That's too big actually. And then this transistor actually, the carbon nanotube transistor. The second revolution only to come in 2004. Then this carbon nanotube transistor got birth. So this is the transistor. Similarly, hydrogen storage. Hydrogen, you see, hydrogen is a fuel. It's a very important material, but you cannot carry on board. So you require material to storage it. The magnesium hydride, sodium hydride, these materials where you store the hydrogen, but in this carbon nanotube is also a very good material for hydrogen storage. So researches are going on. And then lastly, you see the field emission devices. The carbon nanotube is used for field emission purposes. Though the people we have not succeeded finally, we have not commercialized these type of things. But only this Samsung company has already this type of screen. And see, the principle is very simple. Class 12th principle you see. So these are our different panel for display devices. You have a LCD. The first one is a cathode ray tube. We are very well aware with the cathode ray and the liquid LCD and the plasma screen and all those things. But if you see, the merits of the field emission are very high as compared to the LCD and other things. What is field emission? Just see, field emission is very. We are teaching to the students. In devices, in field emission devices or the devices, what is simple principle is that you eject the electrons. Electrons will fall on the screen and your screen will be bright. This is the basic principle. You have to eject the electrons, and there are 4 methods we teach to the student in BSc or BTech in first year: the thermoionic emission, the field emission, the photoelectric emission, and the field emission. These 3 things we are doing experiment also: photoelectric effect, thermoionic emission, you can say, bulb and other things. And then we are simply teaching the field. If you apply field on a conductor, can electron will eject out? No. But you apply a very high field, let's say 1 lakh volt, electron may come, may not come. Because you have to create a very high field to eject electrons. But the carbon nanotube has solved. Let us, for example, you are applying, you can say, a field of, let's say, 1 lakh volt, that is 10 to the power 5 volts. And distance is only, let's say, 1 centimeter, the field will be 10 to the power 7. On the other hand, you take carbon nanotube, apply 1 volt, then 1 upon 10 to the power minus 9 or 8, it is the same field. So whenever you apply a low field on carbon nanotube, a large number of electrons come out. A stream of the electrons will come out that will fall on the screen will be more brighter and like that. So that is them. So electrons are there. You have seen the carbon nanotube. The network of the carbon nanotubes, electrons will come out, they will fight each other, interact. So for that purpose, we require aligned for better. So these are is first example of carbon nanotube. That is, and this is our setup for. This is the schematic diagram. This is our setup for measurement of field emission, and this is the other setup, and that is a prototype of things of field emission from our lab. Now, other medical applications you see. The medical applications of carbon nanotubes, that MRI pictures. When we take the MRI picture, doctor will give you some toxic things, and then they will take the MRI. But when you encapsulate particularly the gadolinium ion, and in gadolinium ion, when you encapsulate this gadolinium ion carbon nanotubes and you take the MRI picture will be more bright, more contrast will be there. So this is the example of carbon nanotube. Similarly, we can do the genes therapy. These carbon nanotubes can be functionalized. You can attach a functional group. So, in your gene therapy, see your DNA, which carries the genes, cannot pass through the cell membrane. This is the problem. So, what we do, we functionalize the carbon nanotube and by amino group, and that group will be positively charged, and your DNA backbone has negatively charged. So, there will become hybrid of DNA and nanotubes, and that will pass through the cell membrane. Like this, you can do the gene therapy and create and effect. Similarly, bones actually, they are trying that to dissolve carbon nanotubes. A very ultra short carbon nanotube can be dissolved, and then have a solution type of things. Suppose there is a means severe accident, and then mashing of the bones. The doctor will do the operation and put the bones at right place and may inject the solution of the CNT if it is possible. Then it will be after sometimes they will be so strong. If you want to break up these bones by hammer, you cannot break up. Similarly, cancer treatment. The cancer treatment is also the experiment is going. What is the problem with the cancer? The problem with the cancer is that your cell is not small. That is very big. And to means you want to destroy the cell. So you require a probe smaller than cell. You do not have at present the probe smaller than cell. That's why it will spread out. So the carbon nanotube much smaller than the cell, and there is a property that if you put infrared laser on carbon nanotube will get heated. So now see carbon nanotube, they will put infrared laser, they will heat up, they will burn the cancer cell. So these are some important applications of carbon nanotubes. Now come to the other part. In our group, we are also doing the dynamical response of non-linear vibrations of single wall carbon nanotube. It is a collaborative work with a mathematics professor from our university, same university. That is, they are doing some modeling and simulation type of work. They are explaining that these non-linear vibrations. The idea is that the physical idea is that when you are taking these carbon nanotubes for device applications, so you must know this is what is the age of carbon nanotube. After some time, what will happen there? We call it aging effect. So mathematically, they are saying that after a certain period, there is the possibility of the chaos in the structure. So that might be the aging effect, but things are not very certain. The people are working on that. This is our group. Now there is another thing actually, a very means a disease, arteriosclerosis. The arteriosclerosis means in your bones, that means in your arteries, you have a high level of cholesterol. When you give the drug will not reach to the right place. You give more drug, your patient will die. So that is a problem to send the drug in appropriate amount to the particular place. So we cannot send it. So what we'll do, we take the help of nanoparticles as a carrier, and particularly for this fumagillin drug is used, and so this is the applications of nanoparticles like that. There is another application of the nanoparticles is that you see the cracks. Cracks may be in bones, cracks may be in the building. Cracks remain always cracks, are always crack. How to banish this crack? You can fill the nanoparticles. Nanoparticles have the property to orient themselves. So this is also one of the applications of these carbon nanotubes. And now our group is working. These are a lot of papers we have published in this area. And we are running a MTech nanotechnology program. It's a commercial track for young people, that is students. That is the nanotechnology 4-semester course and 20 seats in all branches from engineering and then MSc physics, chemistry like that. There are the certain laboratory equipment which we are having in our lab, that is sputtering systems and nanostructure thermal operation system, LPCVD, ECR-CVD, then PCVD. This is the whole element already I have shown. And then we have other equipment, and finally cell, and then FTR, and all recently we have installed that HRTech, HRCell, HRXRD, RF sputtering, very sophisticated RF sputtering, because for carbon nanotube depositions we require the thin film of 10 to 20 nanometers, and then microscopic nanotubes. So these things are at the center, and the center has been developed. And then our basic means target is the single wall carbon nanotube and their semiconducting applications, and we are working on sensors and other applications like that. And whenever we give the talk like that, that you see here, many things are not still mature. The things are at research level, and some people ask where is the hospital, where is the cancer treatment and other things. Our answer is that good things comes in small packages. Thank you.
Thank you, sir. I think we can have a small discussion session, interaction. If anybody is interested to ask, yeah, please.
Yes. No, that is okay. We say that graphene or the carbon nanotube is the rolled means graphene. That is initially we were used to say, and that is particularly these we categorize the zigzag, armature, and all those things for single wall carbon nanotube. So this is the idea. That is how you roll. You are not rolling actually. Experimentally they are already there, because when you have the things may be semi-metal, maybe semiconductors, maybe insulators, these type of things. From that we see the structure, and we categorize into different three parts of these tubes actually. It is not already we do not have any trick that we can have a particular type of we search in that. Not further to, there are number of methods. It's not two. Some people are making from different other style, means these carbon nanotubes by different type of carbon like that. It's not two only, there are number of methods. Some people are making from some chemical roots also. Photolithography actually. The lithography is means you see these carbon nanotubes, and the carbon nanotubes you can just put over that. The lithography, see, lithography is a different subject, where you put printing like things, and photolithography, dip pen lithography, and then X-ray lithography. There are some all the things to prepare your samples and like that, and then. So it's a big topic, separate lecture, 4 or 5 lectures, then you will understand these lithography systems.
Somewhere in the internet I have studied about the stone
The stone?
Stone with deformation, where the carbon layers of carbon they are closed by some gaps in their edges.
I could not follow the question.
Sir,
Achha, Amrikesh can see. Yes, this is possible actually,
for petals they were transformed into for petals they are transformed into heptagons and two pentagons. I do not understand their defects. Actually, I would like to know the defects.
So actually defects and all these things you have to go for characterization. You go for SEM analysis, TEM analysis, Raman spectroscopy. Defects generally we study from Raman spectroscopy, D band, G band, and all those things. So from that there are two bands, D band and G band. And if you see the height, the intensity of D band and G band. G band, if D is very small, then your defect free means the carbon nanotube or defect. So that is Raman spectrum, by which we see these defects of those things.
Having some parameter to control by which you can get these aligned nanotube.
Yes.
So is it simply by chance, or you have some this control over the parameters by which if you very carefully you set those parameters during the experimentation, then you will get this?
No, actually, see, it is not by chance. One thing is called skill. So it is a skill actually, you develop the skill, but there are so many parameters here. Number we have three gases: the gas pressure, the catalyst temperature. There are number of parameters. So you just go. So there is another thing. If you go for modeling and all thing, you can come nearby to that, right? It is not means just arbitrary things.
With your experience,
Yes.
you come to know that if I keep these parameters within certain limits,
Yeah.
so there is a very good chance of getting the aligned.
Yes, and that's a difficult task actually. And particularly for these field emission properties, we require aligned carbon nanotube. And the aligned carbon nanotube which we have grown, hardly, I will not challenge, hardly you will find in any literature such a beautiful aligned carbon nanotubes.
Most of the time you said that you get this normal
Yes.
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 So like the applications of the jumbled where do we have that?
There are number of applications. This is jumble type of things, no? Sometimes we require, these are when we grow on silicon wafers. And if you see what is the yield is very small. But we want is yield very high. You have that is first method is the discharge, hard discharge. Hard discharge you can produce in kilos actually, and you can use for nanocomposites. You can mix in plastic, you can mix in polymers, you can mix in other materials, and so the nanocomposites is bigger. And nanocomposites are required at various places, just strong bonds. You can go for tires and all those things. So there are a number of applications of nanocomposites.
Sir, I have one question.
Yes.
Sir, actually, which vacancy is more preferable in carbon nanotube, mono vacancy or divacancy?
Preferably means vacancy.
Which it means generally what we find in the carbon nanotube when we do irradiation techniques, some kind of carbon substitution or all those. So generally, what occurs, whether it's mono vacancy or divacancy?
No, you are saying about the I think you are talking about the you can say the functionalization of the carbon nanotube.
Functionalization defect. So defect
So
in
functionalization is also like that.
Okay.
You are telling one group or two group like that.
Yes, sir.
So it is the way means it is possible. Though I have not done functionalization type of business actually, and then generally one or two you can functional group you can attach, but preferably it is one.
Okay. So if no further question, let us thank the speaker. Thank you so much, sir, for illuminating us with carbon nanotubes and its all various applications and what are the various possibilities for the theoreticians basically. So we have the next speaker is Professor Ravi Pandey from Michigan Technological University, USA. So may I invite you, sir? I'll just connect your label.
So let me start when Rag and we can set up the thing. I've been working in research as a student to faculty member almost 30 years. And I'm doing two things for the first time in my life. First thing is giving a talk on Sunday afternoon. And the second thing is skipping the cricket match. I'm still passionate about the cricket, but I think for Anurag, I think I can do it. So your affection is pushing us to do it. So I just slightly changed the title, depending on the remarks of Dr. Hussain about the modeling and how does it relate to experiments. But in a nutshell, like he said, the physicists only do the conduction. And my idea is to give you a glimpse of how can we calculate the device properties using now is called 2D materials. So Dr. Hussain's talk was excellent introduction to nanotechnology. And the message is what in the second slide I think he said is what we are playing with is a delocalization of the valence electrons. That's the key thing. And we have few questions about how to make some defects, some vacancies. All is the interplay of these valence electrons and what is the extent of delocalization. So that's, I think, is in one line, is the crux of this nanotechnology. These are 1D or 2D materials. And I'll show you some examples how to manipulate this delocalization to get the tailored electronic, magnetic, or optical properties. So my aim is to sort of convince you, and I think since you are here, you are already convinced about the modeling tools. But the message is I think we should be giving to audience and also the experimentalist that we need their help. And you can see here the help is in terms of we have to first judge the how good our model elements are. Right? It's a benchmark. We have to do it, and only we can do it when we have the experimental data is available. So what our idea is to have this capacity on two grounds. Is of course we have to judge the validity of our model elements, but then go on and provide a means of the resolving questions. What's going on to help experimentalists. And if not, if you feel good, then go on and sort of provide the guidance. That's the key thing is what we can do is provide the guidance, work as a filter for experimentalists to reduce their data points or the processing parameters. So that's the message I would like to give. So let me tell you about these tools. What we have is you can go. This is the time scale, and this is the distance. And if you go meters to years, we have the tools for engineering. And Dr. Deshmukh can see the finite element method is here also. It's part of the whole spectrum. And as we come down, so what we are looking at in this workshop is talking about the molecular mechanics, which is in terms of the nanometer versus nanoseconds, mainly the atomistic techniques, the molecular dynamics, modeling of force field methods. And then we have so-called the tools based on the quantum mechanics of Schrödinger equation. I think Professor Aulak is not here, which is supposed to give a talk on DFT, but I think Mrinalini Deshpande is giving a talk on the first principle methods tomorrow morning. So I'll skip the theory part and move on to only applications. To show you where I come from, originally I'm from Sagar, which is nearby, again Madhya Pradesh. After getting masters, moved to Delhi and BL, worked there, experimentalist. But then move on to do PhD from Canada, and I've been at Michigan Tech for last 20 years. And this is always in Michigan, but we are far away from our capital city, Detroit. But we are closer to Chicago or Minneapolis. And there's a very nice lake. Sort of this town reminds me of Sagar, my hometown. It's a beautiful lake, and the only disadvantage is we get a lot of snow. And I think Mrinalini can attest, our average snowfall is 200 inches every year. So graphene is coming from Dr. Pandey's slide, is from Allahabad, now is in Jhansi. Like the slide is about, is we start from original size, is again go on to optical microscope under it, look at the electron microscope, and indeed is in STM, you can see sort of the hexagons forming this 2D carbon hexagonal sheet we call graphene. I think most of us know it's a good material. It's made of carbon, of course, so it's going to have a sort of the strongest sort of strength. It's transparent, bendable, and also conductive. But the key thing is about the device applications. Can we use graphene for devices? And as we know, is graphene had, if you look at the band structure, is what we call is semi-metallic. At certain K points, the band gap is 0. And in order to have a application for transistors, you have to have a finite band gap, which may be small. And this is the measurements which sort of provides you the sort of experimental setup which provides you how high the electron mobility is. And you can see pretty high, it's coming out. This is called 6 probe. And you can see this is the graphene sheet width and then without. And this is the sort of experimental setup where we have measuring the electron mobility in this material. So the question comes in is how to induce the gap before we move on to use it as a so-called field effective transistor, because a finite gap is essential, but we don't want to change the mobility because that's the strength and of the material. So people have come up with ideas, especially coming from experiments. This is sort of a monolayer. Let's have a bilayer graphene. And what you can see here, if we apply the electric field perpendicular to the surface, this is the pristine when the electric field is 0. But once we apply the electric field, you can see it sort of induces a small band gap. And exploiting this opening of the gap is the scientists have made the devices based on this bilayer graphene. And you can see this image, the optical microscopy. You have this is a source drain, and this is a top gate, and you can see this is a bilayer graphene, which you can see this in the schematic diagram, which does work sort of as a transistor, where you can modulate the current by applying the gate field. But again, we have to find another way also, because electric field, application of electric field in a bilayer graphene is not an easy task. In order to make a commercial device, commercial transistors, you had to move on to some alternative ways also. So our idea is what is the reason of the band gap opening when you apply the electric field? So what you have is electric field, so you have a first layer and second layer. The electric field, you can see the magnitude of the electric field for the first layer carbon atoms and the second layer carbon atoms is different. So the polarization which induces this electric field, so what we have is so-called dissimilarity in the carbon lattice. And this dissimilarity can open up the gap. So idea is, let's not apply electric field, let's not have a carbon or graphene layer, let's introduce a second material and see without applying the electric field, can it induce the band gap? So, as you know, is boron nitride is close to graphene in terms of the structural properties, but it is a big, large gap. It's about 5 eV. So our idea is look at it. Let me go back. I think it's to different sort of what we call stacking, and bring in for the graphene vicinity of the hexagonal boron nitride monolayer, and let's see if it can provide the answer which you are looking for. So before doing it, as Dr. Hussain said, is you have to see, can someone fabricate a boron nitride monolayer? So we looked in the literature, and we did find this back in 2009. You can have a different monolayers or different layers of boron nitride, and from here you can see is you have a 0 is a monolayer, then you have bilayer, tri-layer, and sort of a 4 monolayer system. So yeah, someone can grow it. So you feel good. What theory or modeling you're going to do is going to have some relevance in a device physics area. So let me switch gear and then talk about a little bit about modeling elements, which I think Mrinalini will cover tomorrow, exactly what they are. So we are using a so-called first principles method, testing functional theory, where we can write the total energy of the system in terms of the electron density, not the wave function, but density. And there is a Condensed theorem that if we have a very good electron density, you can calculate the ground state properties of the material very, very accurately. That's the key thing. But we also add another layer of approximation because these are the layered systems. Especially the graphene is so-called the graphite, the multi-layer graphene system is bonded by van der Waals forces. These are the long-range forces and what we call the dispersive forces. In a sense, they sort of, the magnitude comes down on the degree of polarization in the lattice. So you have to perform a standard DFT calculations, but in order to do an accurate calculation, you have to add this level, another approximation to your modeling or simulation areas. We have been using both siesta and WASP, depending on what we want to do. And then later on, I'll show you some of the results about the electron transport. We have studied the electron transport in both STM-like configuration and device-like configuration. And I think Anurag Rodrigo will talk about it. And in the next talk, one of our colleagues will talk more about NGF. So how important this van der Waals correction or inclusion is. So typically if you compare with so-called local density approximation, you can see it does reproduce a very, very accurate inter-layer spacing between two graphene bilayer system or a graphite system, graphitic system. But what it does not do is sort of, you can see, produce the accurate binding energy per atom. So you can see here experimentally measured is about 52 MeV and LDA only gives you 17 MeV. But once you add this empirical van der Waals correction, we sort of come up to very nicely about 45 MeV, which is close to experimental value of the binding energy per system for these systems. So for the layered messages, for the layered system, you have to have a van der Waals corrections in order to get the good binding energy. Not the lattice constant. Lattice constant you can get away with either LDA or GGA. That's not a problem. So let me skip it. So let's see what happens. So we have a graphene and we bring in the boron nitride. And most of us know is you have to play to find what is the equilibrium configuration is. So you do so-called Bernal AB stacking, AA stacking for these two cases. And once you have the equilibrium configuration, let's look at the band structure. What does it do? For the reference case, we have also picked up the boron nitride because we know boron nitride is semiconducting. So can boron nitride be in monolayer or bilayer form is semiconducting? So you can see here is a nice gap for monolayer, and this is a bilayer, again a nice gap. So you do have some confidence, is indeed our modeling elements are reproducing the characteristics of boron nitride very well. This is the graphene. You see here is a nice Dirac cones coming out, so zero gap for this material around K points. And if you bring in a graphene with the boron nitride in the equilibrium configuration, and what you can see here is indeed we reproduce the Dirac cones and coming out also the features from the boron nitride. But if you look closely at the K points, indeed we have a small gap. So it seems our hypothesis did work. Is what we have is once you bring in the boron nitride monolayer, it does do something to the system, giving you a finite gap. Now question is why? What is happening? So we look at the so-called valence bar charge densities. And you can see here is on the left you have boron nitride, nicely covalent bonded system. And then you have graphene. It's a metallic-like charge density. And so what is coming out is definitely this carbon atom sitting at this top layer looking at the boron, and the other carbon atom is looking at the nitrogen. So in the carbon lattice we have dissimilar charge density, which then induces the band gap. And it seems our hypothesis is correct. But can we prove it? Because you have to go in and talk to experimentalists, say this is your hypothesis, you have seen it, can you prove it? So our idea is, okay, let's see what happens is we have the equilibrium configuration. If we sort of either bring it closer or move forward further, can we modulate the band gap which is open due to this inhomogeneous charge density? So this is the slide. So if you can see here is we start from the equilibrium configuration, and I call it a strain. Basically we are bringing in these two layers closer and closer and closer. And if this inhomogeneous charge density hypothesis is correct, it's going to have more and more inhomogeneity, and it's going to open up the gap further and further. And you say, waha. If you look at here, if you start from a reference case, by only 10%, sort of variation in the interlayer spacing, the band gap has sort of almost doubled. So what is coming out is, in terms of summary, is indeed our bilayer system with graphene boron nitride. It does have a so-called graphene-like features, but it does have also a small band gap. And this is, nothing is coming out because of the interaction between carbon with boron and other carbon with nitrogen, giving a sort of inhomogeneity in the carbon lattice. Let's look at the next step. It's the trilayer system. And this idea has again come from Ralph Scheiker, who was visiting us, a postdoc in my group, and I think he's also part of the conference. He said, Ravi, let's look at the trilayer system. Because we know is, and Dr. Hussain also said, is synthesis of a monolayer or bilayer system is not easy. Like I said here, single wall carbon nanotube is not easy to grow. Multi-wall you can have. So thicker the sample is easier for experimenters to grow the devices and make the devices, fabricate the devices. So now we are looking at the trilayer system. So our idea is we have two graphene bilayers. Let's insert boron nitride. See what happens. And vice versa, if we take the two boron nitride and insert the graphene, and look at the transport or band gap properties is what is going on. So let me skip it because we do all sort of optimization is how to find both called ABA, ABAAA and ABC stacking, and generate especially if you have a very good student, he finds all the different configurations. But let's look at the results which are summarized here. In terms of the band gap and what happens when you apply the electric field perpendicular to the surface. So on the left, you can see here is I have this graphene, boron nitride graphene system. And as I go electric field from 0 electric field to so-called 1 volt per nanometer, the gap varies linearly nicely and saturates. And that's what the experimenters would like to have it, is not the sort of a linear variation in the gap with electric field, because there has to be some saturation so they can control the device characteristics. In the reference case, we thought, let's see, look what happens in the bilayer case. It's a nice linear curve with a sort of a smaller gradient. And if you look at the other case, we have two boron nitride and graphene is inserted between, nothing happens. And we further go down and look at the case of this two graphene and boron nitride, and these are so-called the different stacking. You can see they have a different variation. So what we have is the variation in the trilayer system, which depends on the topology of the system, and is only true when a boron nitride monolayer is inserted between two graphene. So this is again is a filter. It's a guide to experimentalists if they would like to make a trilayer device, sort of a fabricate trilayer device system, then it's better to use two graphene with boron nitride in between, or vice versa. Why? What is happening? So if you look at it here, is the boron nitride graphene boron nitride system is our valence charge density is dictated by on the graphene sheet. And it comes back to again is Dr. Hussain's first slide, is a delocalization of valence electrons is a key thing, no matter what you do. But if I have a two graphene and boron nitride inserted in it, you can see the extent of delocalization on both top and bottom layers. And that's why we do find a variation for the system where we have a boron nitride inserted between two graphene monolayers. Makes sense? So this summary is we have is indeed is for graphene, boron nitride, graphene. We have again is almost zero gap. Different topological sort of variation gives you from 1 to 6 MeV, which I got about a zero gap because this is within the bar of our calculations. But it does have a modulation of the gap, which depends on the topology. And other way around is for boron nitride, graphene boron nitride, we do have a sort of a large gap, but again its electric field does not show any modulation. So this is about graphene and boron nitride systems. Let's look at beyond graphene. And this is, I think, is one of the weakness we have in US. In order to attract funding, every 5 years you have to change the field. That's a big problem. So it started with say fullerene, carbon nanotubes, graphene, and now the buzzword is beyond graphene. If you submit a proposal with carbon nanotube, you will not get the funding. That's a fact, but so be it. So we are looking at in our group is a lot of different variations. I'll show you some results on boron nitride. Dr. Hussain mentioned about the molybdisulfide. So we do have some results on molybdisulfide. And then we have called silicene, based on again is silicon or germanium. And recently we also have started working on called phosphorine, which recently we published one result with Anurag, which I'll just skip it, and we can talk more about it in private. So this is molybdisulfide, very interesting material. I think it's much more stable and much more important to me as a modeling person than graphene or other tuning materials. And the reason is it has a so-called non-centrosymmetric sheet. So although this is the monolayer, you can see here this is the monolayer, but it's composed of 3 layers. Your sulfurs are sitting on top, and molybdenum is sort of in the middle, and it can have two types of coordination. What we call is a trigonal prismatic or octahedral. And that's the fun part. If symmetry is broken, you can definitely exploit the different properties, the variation in the properties for any applications. But as you know, as a computational scientist, the problem is if symmetry is broken, we have to have a larger computers. Because then when you calculate the integrals and other stuff, it goes into power 4. But that's fine, we'll see how can you do it. And second advantage is this is semiconducting, about 1.5, 1.6 EV, which is again is manageable for electronic applications. This is again is very easy to synthesize. I don't know if you are doing Dr. Stan in your group, but again one can do Scotch tape, what they call, or CVD approach to make molybdisulfide with layered materials. So again, the student came up and said he wanted to work on molybdisulfide. So I asked the student to go out and see what has been done. So he found a very nice paper. This came out in 2013. Look at you have a pristine molybdisulfide and you deposit the gold nanoparticles. And what you can see advantage here is this is a current source drain and this is a applied voltage. In this case is a back voltage, is a gate voltage. And see, so for the pristine molybdisulfide, you have a nice flat curve. There is no change because again it is semiconducting, 1.5 EV gap. But once you deposit the gold nanoparticles, you can see after about -6, this gate voltage shoots up. It's about what this claim is about 10-fold enhancement in the gate field. So our idea is, that's fine, is a gold nanoparticle is not easy to deposit. You have a lot of variation in the gold particle sizes. So how about having a sort of a gold atomic wire? And see if you can do some calculations, some modeling to understand its effect, and then move on and tell experimentalists could be the atomic wire is a better way of enhancing the gate field current compared to the nanoparticles. So a student from Shimla came to my group and he started doing it. So let me go for this slide. As we know, is the problem for us is if you come, we have a molybdisulfide sheet which is a lattice constant about 3.2 angstrom. And I'm again simulating the atomic wire on top of the sheet. And if you look at the atomic wire lattice constant, going from 2.6, 2.4, 2.5 angstrom. So if I do it, my experimental friend will come and say it's not possible. The problem is a big lattice mismatch. You get a lot of strain in the system, but it's not going to be stable. So the way around is less to use so-called supercell approach method. So instead of a 1 by 1 atomic cell, just use a larger atomic unit cell. The cost is computational cost. It's going to go up, but that's fine, we can handle it. So what we are using here is so-called 5 by 1 for atomic wires and 4 by 4 for sheet. And once you do it, you can see is mismatch is less than 6%. It is noticeable, especially for the copper, which is the case here. But at least we can get some kind of guidance what happens if we have a copper, silver, gold, and platinum atomic wires on MOS2 sheet. You do the same thing is the binding energy, you have to find the equilibrium configuration. And what we find here is, interestingly, is this copper, silver, gold, they prefer so-called hollow side. In a sense, they sit, this atomic wire, atomic wire sit sort of in between. But for platinum, it loves sulfur. Okay. Platinum sulfur bond, which I did not realize before doing these calculations. I thought gold sulfur bond is one of the strongest bond, but platinum sulfur bond is much more stronger than gold and sulfur bond. And it sits on top of it. Once you have it, you get some energies, and then see what is going on in terms of the physics and chemistry of the system. So here we plotted for the equilibrium configuration for all the 4 atomic wires sitting on top of the MOS2 sheet is what kind of bonding they are forming. So we know is silver and gold is nicely, is their S-type sort of elements, but for copper and platinum. So what is coming out is again is the guidance is to experimentalists. If you have a d electron atomic wire sitting on MOS2 sheet, it's going to be strongly bonded compared to either S or P electron system. That's the message is coming out. And you can see here is sulfur, copper, and especially the platinum atom sitting with the sulfur, and even the molybdenum. Very, very strong bond with the first and the second layer of the sheet. Let's look at the now electronic property. What we expect is once you have that atomic wire in the system, is tend to be metallic, because these metallic atoms induce a finite density of states near the Fermi energy. And this is what happens. For platinum, again you have very nice sort of a magnitude of the finite density at Fermi. The dotted line is the Fermi energy. And same if you have a less or more of gold, silver, copper, and this is a pristine which has a nice band gap of 1.5 here. But what we notice here is if you look at the platinum, the finite density of states is at the unoccupied side. For the other atoms, is more or less is towards the occupied side. So if you do a next step, which I asked the student to do is, let's do the electron transport. Assuming we have a scanning tunneling microscope setup. Okay. Because these variation in the density or location of the density of states at Fermi level is definitely going to affect the electron transport properties. So let's look at the STM-like setup. This is a nice substrate we have. You can use anything. Then you have the monolayer, and now it's a functionalized monolayer in our case. Distance you keep it about 3 angstrom, which you do again in the total energy minimization of the system. And then you have a tip. And for our case, we use a gold tip because it's easy to use it and it's faster convergence because the S electron. And the key thing is, like I said before, it basically is the overlap of density of states, the tip, and the monolayer. Basically gives you the qualitative description of the tunneling current. You can see nicely comes up in our current voltage characteristics. So you have a current flowing through the bias we apply. And you can see here this is zero bias, we go both positive and negative. And for positive bias, of course, you expect sort of a linear variation because of we have the metallic finite density of states as Fermi. But for platinum, which has the magnitude is higher towards more unoccupied side, so what happens is as we apply the negative bias voltage, the unoccupied density of states come into the play because you are occupying them. And you can see nice, very enhanced current with possibility of NDR effect. It's a negative differential resistance effect. I say possibility because we have not gone through the case, because this is, we are talking about electric field of 10 power 8 to 10 power 9 volts per meter, which is very, very high. It's close to breakdown voltage. So the message coming out is pristine MOS2 is semiconducting. The functionalized MOS2 is conducting because of the density of states due to metal ions. And this asymmetric current voltage is simply coming out of density of states. Difference between a platinum case or copper, silver, or gold. Then you can again plot, because I call these pretty pictures. And to show our experimental friend that we also can have pretty pictures. But the key thing is because of the difference in chemical bonding between platinum and other elements, you can have a nice distinguished feature for platinum, but not for the other elements. So what you can use is these sort of calculations as again to guidance, to experimentalists, as a fingerprints, that if we have a platinum wire sitting on a MOS2 sheet, it's going to have distinct features compared to other noble elements. So let's move to, I think I'll skip because we have a lot of other things to go, but we have also done some work on quantum dots, and our idea is to look at the triangular flakes, nanoflakes of MOS2. And the difference is the typical experimentally synthesized flakes are about 10 to 20 nanometers, and we have done a very small set, about 1 to 2 nanometer size. But what does it come out is indeed in nanoflake, because of again, if you remember the first slide, is if it's so small, the electron density is completely delocalized. So although the sheet or the bulk of MOS2 is semiconducting, but these nanoflakes, the triangular flakes, are metallic. And one can use for different sort of electronic or spintronic properties. So let me skip it. And then come to now is nitrides. As we know is from, again, the bulk studies in our group and a lot of Dr. Ahuja's group, and Rog has done a lot of bulk studies, is 3,5 nitrides are stable. We know we can fabricate a zinc bland boron nitride monolayer, but what about the other nitrides, especially the gallium nitride, because we know it's a very good blue LED material. They have a nice gap also. So the question is, I asked my student, is can we sort of, again, is a thought experiment. Okay, that's I think is we have advantage over experimentalists, is we can do a lot of thought experiments and see if we can find some interesting physics, although the gallium nitride 2D material has not been fabricated yet. Okay. So we thought, let's look at it is compared to boron nitride and see if we can make gallium nitride on our modeling a supercell approach, what kind of transport property is going to have it. So pick the 2D sheet, and again is you can have optimize the variables, which is more or less same. You can see nicely the 2D sheet of nitride material follow the pattern what we have in the bulk. Is boron nitride is a very strongly covalent material. Move to aluminum nitride. It's nice circular spheres because aluminum nitride is much more ionic compared to boron nitride, and gallium nitride is in between, is semi-ionic, semi-covalent material. So the chemical bonding persists in the 2D sort of a low dimension 2D phase related to the bulk phase. Band structure, again it comes out semiconducting. We have a nice gap for gallium nitride, aluminum nitride has the larger gap. And of course, boron nitride has the largest gap, and in 2D monolayer case. The question is let's look at if we can make devices, because these are simply the band structure calculations. And if you go out and talk to experimenters, says it doesn't mean anything, okay? Because device physics is much more than simply materials physics. So we thought, let's do, and if we can do some calculation mimicking the devices. Let me skip this part quickly and come out to asking the question, because we know that the single layer nitride, that the boron, aluminum and gallium, has a large gap. So can they act as a good dielectric material? That's the question we're going to ask. So you have to have again a device setup. So this is the typical device we use. This is our monolayer. We do optimize so-called Ds. How far is it? And these are the gold contacts. And what you see here is we are talking about, I think Rodrigo will talk more about the theory, and he was the one who did a lot of calculations in our group, is the convergence problem. So we have this quantum mechanical region, which is our monolayer nitride, but then we have a semi-classical, semi-infinite, the contacts, left and right. And the question is how to deal with it. Because our wave function in the monolayer does not see the enough Pauli's repulsion at the contacts, the boundaries. So it tends to bleed. And then you have a problem of convergence in these type of calculations. So one has to go beyond a single layer to at least 8 or 9 or 10 layers of gold atoms to contain this quantum mechanical wave function in our scattering regions. This is another sort of look at this view of our device structure. I'll skip the theory part because Rodrigo will talk about it. Let's look at the results. And when I looked at it, I told my students something's wrong. He came back after 3 months, I said something's wrong, literally. And after 6 months he said, sir, this is the result. Now can you see what is wrong with it? It's all our material system, they are semiconducting. Okay? But once we apply this bias in these devices, left and right contacts, look at the current. The boron nitride, gallium nitride. And this is our graphene, which we know is graphene semiconductor is a semi-metallic material, and boron nitride or gallium nitride are semiconducting. So it should be the other way around. Look at the transmittance. So you see here, graphene is very little at Fermi. The boron nitride and gallium nitride, very, very high. So once we've seen the results, we have to find out why, what is happening in the system. So this is the result, is monolayer with a gold contacts. Gallium nitride is a much higher current than graphene. And then if you when I talk to my experimentalist friend, he said has to be an interface effect. Is at the contacts, when the gold makes a contact at the boron nitride, aluminum nitride or gallium nitride, it has to be the key to give you this calculated current, which is much higher than what you expect from graphene. So our idea is to let's see if we can nail it down to interface effects. So we'll look at the device configuration. We have simple density of states, and they mimic what we have in a transmittance. Is the boron nitride connected to the gold. You have a large peak here. Graphene, of course, you can have it, and gallium nitride is a large peak. So it does follow is current is going to be high in gallium nitride compared to graphene. So we have a tool called projected density of states. Let's look at the composition of these density of states at Fermi. Then you can chart it out. So if the interface effects is important, so at the equilibrium spacing, which is 3.1 angstrom, I have it. what happens if I move my contact further and further away? Okay. And this is again a thought experiment. So idea is, if contact is far away, I'm going to have a less interfacial effects, interface effects due to this large distance, as is in the equilibrium space. So that's what we are doing here. This is a pristine case, no contacts. You can see nice Dirac cone, and then you have a gap in boron nitride. We bring in the contacts. You can see here, depending on the case, is depending on the left and right shift. And as you know, the magnitude of the left or right shift gives you so-called doping level. Okay. And what we see, interestingly, is for graphene, which everyone expects, is an N-type material. But for boron nitride, it's the other way around. This is coming out as a P-type doping induced by the contact, and it varies with the distance. So what is, we are coming down focusing the reason is the calculated current for boron nitride is much higher than graphene because doping is different. It's a Y-type material or P-type material. We go further to the transmittance. Okay. On top we have graphene. So we are going from the contact distance from 3 angstrom to further 4 angstrom. And graphene is semi-metallic. So you do expect some transmittance or some current at 4 angstrom. And you can see here, as you go down, it still has the finite peaks. But if I move from graphene to boron nitride, at equilibrium spacing, we have, look at the large finite transmittance. If I go further, it goes down, and at 4 angstrom, which is further away, you can see it's almost 0. So what is coming out is the coupling at the interface is very, very important. And you can see here is the electron charge density, the boron nitride gold interface and graphene gold interface. This is the electron density sitting at the interface. In the boron nitride case, we still have a higher current because of, again, this interface. The effects coming out of the gold atomic orbital, or what Dr. Hussain calls it gold delocalized electron density, is hybridizing with the delocalized electron density of boron nitride, giving a large current. This is okay. Then friend asked, if your thought experiment is okay, means you're going from 3 angstrom to contact distance 4 angstrom. What happens if you have a more than one monolayer? Okay. Can a 4 or 3 monolayer boron nitride mimic semiconducting property? So I thought, let's do it. See, here is the graphene, and we have a monolayer which is in black, nice finite transmission. You go to bilayer and trilayer case, you still have transmission at 0, which you expect. But look at here, boron nitride. Monolayer case is such a large hybridization of gold and boron nitride electron density orbitals. Bilayer case, it goes down, and trilayer case, there is no transmission. It mimics like a semiconducting material. So the message is indeed monolayers of graphene and boron nitride, they do have similar transmittance characteristics when they are connected to the gold in a device characteristics. Although the pristine graphene is semi-metal and boron nitride is semiconductor. But the good news is indeed, if you move on to so-called multi-layer systems, it does show so-called exponential dependency of transmission function. And of course, graphene does have a very high tunneling probability. So what the message is coming out to experiment is, again, is a guidance. If they would like to use a monolayer boron nitride as a dielectric material, they may have some difficulty. So they have to, or again, the suggestion is go beyond monolayer and at least look at the multi-layered nitride system as a dielectric material because of the dominance of interface for the monolayer system. And indeed, if you see, some of the papers have come out, and they did find is a monolayer boron nitride is not a good dielectric material. One has to have at least 6 layers of boron nitride to use as a dielectric material, which is good. So this is the end of the talk, and I hope I convince you is indeed our aim is to provide a quantitative results of such accuracy and reliability that they can be used to predict physical and chemical properties. But we have to go hand in hand with experimentalists. The idea is we can sort of help them to understand the mechanism behind any experimental observations, or we can guide them to work as a filter for future experiments. And I have to show you this slide. As I said, is we get 200 inches of snow. So the students at Michigan Tech, for fun, they make snow statues. And this is a fun part. So this is about an 8 feet snow statue. Every year we have Winter Carnival. Thank you.
Thank you very much, sir, for a wonderful talk on 2D and beyond 2D materials. Question, please. If any. Yeah.
Sir, do we have any new methods for increasing the band gap?
Yes. And I said in the band gap, the one method is applied electric field, bilayer graphene.
Yes, sir.
And the other method is introduce a second material, which is different from graphene. But this is true only for graphene. For MOS2, simply do for functionalization. MOS2 is semiconductor. Once you have either nanoparticles, the metallic, or the atomic wires, you can tailor it to the metallic properties. So there are ways to manipulate or tailor the band gap.
Sir, what are the elements that are used for doping boron nitride sheets or molybdenum sulfide sheets?
Pick anything. You can do anything, but doping is not easy because we have to take out the host atom, introduce it. So what we do in this system called functionalization,
Sir,
you attach it. Like I did talk about this work here, we have done it a few years ago. Silicon boron nitride. Single atom doesn't want to go inside the lattice, it's just on top of it.
Okay, sir. Sir, and one more thing, we even do have boron nitride nanotubes with endohedral compounds like lead oxide.
Yes.
Sir, what are the main important methods or hypotheses that represents the endohedral compound properties or the strength of those materials?
Dr. Hussain, can you answer this question? Boron nitride in a tube, how can you manipulate related to carbon nanotubes? Boron nitride. So I don't know the answer how to exploit it, but only thing is difference is like boron nitride nanotube does not depend on so-called chirality. It's always semiconducting. And carbon nanotubes, depending on your zigzag armchair, you can have metallic or semiconductor.
Thank you very much.
Any other question? I think what we can do, sir, we are already running behind the schedule, and there are e-speakers who will be waiting for the last 1 hour. So we are about 1 hour late. So let me thank Professor Ravi Pandey for a wonderful lecture, and of course Professor Shahid Hussain, the key speaker of this session, key speaker 1, and both the speakers have done their job and introducing the concept of basically the nanomaterials. Thank you very much, sir. So we'll be moving to the next session now in 205, not here. So 205, second floor, B block, right? So in next 15 minutes, we'll assemble here, assemble this at the same place, 205, and we'll start the E session here. Thank you very much.